So learners, you must have learned about the concept of tree in the last session. We have seen certain properties of trees, like every tree on n vertices contains n minus 1 edges, and we have also seen some other properties. In this session, our aim is to discuss some more properties about trees, and we shall see some examples and some types of trees also, like what we mean by a spanning tree, what are rooted trees, which are quite helpful in computer science. So we start with some properties of trees, like this one. The result says that let G be an n vertex connected graph with n minus 1 edges, then G is a tree. So you know that an n vertex connected graph has at least n minus 1 edges, right? And here we are given that if n vertex connected graph has exactly n minus 1 edges, then it is a tree. So to prove this, what we are given? We are already given that G is connected. So we have to show that G is acyclic, right? That is, G has no cycles. So we shall assume that G has no cycles. That means we shall prove it using the principle using the method of contradiction. So we assume that G has no cycles, and then we shall arrive at a contradiction. So we start the proof formally. We need to show only that G is acyclic. So assume on the contrary that G has a cycle C. Now if we remove an edge from C, we get a connected graph with n vertices and n minus 2 edges, right? Because we are given that G has n minus 1 vertices, right? And if G has a cycle and we remove one edge from that cycle, we get a subgraph with n vertices and n minus 2 edges, right? And this subgraph is connected. So this is impossible because we already have proved that a connected graph on n vertices has at least n minus 1 edges, and therefore this is a contradiction. This means G has no cycles, and hence G is a tree. The next result is, if G is a graph with the property that there is a unique path between every pair of vertices of G, then G is a tree. So what you are given? G is any graph with this property. There is a unique path between every pair of vertices of G, and we have to show that G is a tree. So if G has unique path between every two vertices of it, it means G is connected, right? So we have to show only that G is acyclic. So clearly G is connected, and assume that G has a cycle C. Again we are using the method of contradiction. We are assuming that G has a cycle, and we shall arrive at a contradiction. So if G has a cycle C, it means then between every pair of vertices of C there are two paths, right? You know that between any two vertices of a cycle there are exactly two paths, and this contradicts the hypothesis, right? Because we are given that between any two vertices of the graph there is exactly one path, and therefore G is acyclic, hence G is a tree. Okay, now let's look at this theorem. It states that let G be a connected graph, then G is a tree if and only if every edge of G is a cut edge. So it is actually a combination of two statements. The first one is, if G is a tree, then every edge of G is a cut edge. right? And the second one is its converse. That is, if G is a connected graph such that every edge of G is a cut edge, then G is a tree. So the first part, let's prove the first part first. It says that if G is a tree, then every edge of G is a cut edge. So to prove this, what you are supposed to show that you just take any edge of G and show that it is a cut edge. You know that tree has no cycles, right? So any edge of G belongs to no cycles, and hence that edge is a cut edge. So this proves the forward implication. And now we shall prove the reverse implication. So we assume that every edge of a connected graph G is a cut edge, and we have to show that G is a tree. Of course, G is connected, so we have to show that G is acyclic, right? Assume that G has some cycle, but then its length is at least 1, and hence it has at least one edge, and that edge cannot be a cut edge. So this contradicts the hypothesis that every edge of G is a cut edge, and therefore G cannot have any cycles, and consequently G is a tree. Okay, so now let's look at some questions. For instance, look at this statement. It says that every edge of a forest is a cut edge. You have to identify whether this is true or false. So to verify its truthness, you just use the result we have just proved. It's easy. You just look at any component of the forest and look at any edge of that. Every component of a forest is a tree, right? So now you have to consider essentially any edge of a tree, and by the theorem we have just proved, we have seen that every edge of a tree is a cut edge. So this is true. So every edge of a forest is a cut edge. The next question is, so that every non-trivial tree has two maximal independent sets. The word non-trivial is essential here because the trivial tree has just one vertex, and hence it has only one independent set, right? So non-trivial tree contains at least two vertices. So we have to show that every non-trivial tree has two maximal independent sets. You know that every non-trivial tree is a connected bipartite graph, right? And hence it has a unique bipartition. You must recall that a connected bipartite graph has a unique bipartition. That is, its partite sets, say x and y, are uniquely determined. Now, the two partite sets in the bipartition are two maximal independent sets. Why? First, they are independent sets, right? They are maximal because you cannot just increase their size by adding more vertices to them, right? Because otherwise, if you are adding a vertex to one independent set, you are actually adding some edges also in between. So the two independent sets are maximal. Okay, now look at this question. Can a tree be self-complementary? To answer this, just think of some small trees, and you will reach at the conclusion that there are some trees which can be self-complementary. For instance, look at a tree on 4 vertices. Look at a path, say, on 4 vertices, and then just find out its complement. you will find that that complement is isomorphic to this one, the original graph. Okay, now let's look at this question. Let T be an n-vertex tree so that T is a star if and only if the maximum degree of T is n minus 1. So again we have two statements here. If T is a star, then its maximum degree is n minus 1, and if its maximum degree is n minus 1, then T is a star, right? So let's prove the first implication. If T is a star, then its maximum degree is n minus 1. So this is actually true, obviously, because in a star you know that there is a one vertex which is adjacent to all the remaining vertices. So if the tree has n vertices, then there is a vertex which is adjacent to the remaining n minus 1 vertices, right? That means its maximum degree is n minus 1. Okay, because the remaining vertices are just leaves. And now you assume that the maximum degree of a tree on n vertices is n minus 1, and then you have to show that this tree must be a star. So the maximum degree n minus 1 means there is at least one vertex with degree n minus 1, right? That means there is one vertex which has n minus 1 neighbors, right? And now look at any two neighbors. Can they have any edge in between? That is, can they be adjacent? Answer is no, because if they are adjacent, then they form a cycle, they form a triangle with their common neighbor, right? And since T is a tree has no cycles. So the neighbors are non-adjacent, and therefore that tree must be a star. The next question is, let T be a tree with m edges. What is the order of T? So to answer this, you just remember that a tree on n vertices has exactly n minus 1 edges, right? So that means if you are given the number of vertices of a tree, you can find the number of edges in it, right? And of course, if you are given the number of edges in it, you can find the number of vertices in it. So this can be answered using that one, right? Actually, if a tree has m edges, then it must have m plus 1 vertices, right? Okay, now we come to the concept of spanning trees. Intuitively, a spanning tree is just a spanning subgraph that is a tree. And a spanning subgraph, you can recall that a spanning subgraph is one which is a subgraph and has the same vertex set as the original graph. So let's look at the formal definition. Let G be a connected graph. A subgraph H of G is called a spanning tree of G if H is a tree, right? First thing. And second, the vertex set of H is the same as the vertex set of G. So if these two conditions are satisfied, then H is called a spanning tree. For instance, just look at this graph, and if we just remove some of the edges in it, we get this graph. This is a tree. You can see that it has no cycles and it is connected, right? So it is tree. Now why it is a spanning tree of the original graph? Because it has all the vertices which are in the graph. That means it is a spanning subgraph and also a tree, and therefore it is a spanning tree. Of course, this is not the only spanning tree, there can be several, and for instance, this one is also a spanning tree of the given graph. Here we have removed these edges like the outer cycle and some more edges on the inner cycles. So this is also a spanning tree which contains all the vertices in the graph, and it is connected and has no cycles. Now let's look at very important result about spanning trees. It actually characterizes connected graphs. According to this, a graph is connected if and only if it contains a spanning tree. Again, it has two statements. If a graph is connected, then it contains a spanning tree, and if a graph contains a spanning tree, then that graph must be connected. So one part is easier, because if a graph contains a spanning tree, means between any two vertices of it you have a path, which is indeed a unique path, but that doesn't matter. We only need to have a path, right, between any two vertices for showing connectedness. So if a graph has a spanning tree, then it is connected. And now we prove that if a graph is connected, then it contains a spanning tree. Okay, so let G be a connected graph. G is acyclic, then G is a tree, right? So otherwise G has some cycle, and let E1 be an edge of a cycle in G. Now since no edge of a cycle is a cut edge, G minus E1 is connected, right? Because E1 cannot be a cut edge. So removal of E1 from G leaves a graph which is still connected, and of course which is spanning, right? Because removal of an edge does not mean the removal of its endpoints, right? So if G minus E1 has the same vertex set which G has. Now again we have the same situation. If G minus E1 is acyclic, we are done, right? We have reached that G minus E1 is a tree. Otherwise G minus E1 has some cycle, and there exists an edge, say E2 of a cycle in G minus E1. Now again we have the situation, either G minus E1 E2 can be acyclic or it has no cycles. So if G minus E1 E2 has no cycle, then we are done. Otherwise we can continue this process until we get a subgraph which has no cycles, right? And this process must terminate in a finite number of steps. Why? Because G has only finitely many cycles. G has a finite graph, it has only finitely many cycles. So this process must terminate after a finite number of steps, and the last subgraph obtained by this process has no cycles, right? That means it is connected and has no cycle and has the same vertex set as the original graph G, right? Which implies that the last subgraph is a spanning tree. The converse part is easy, as we have just proved it. You just assume that let T be a spanning tree in G, then there is a UV path in G for every pair UV belongs to VG, and consequently G is connected. Now let us look at another important result. Let T and T dash be two spanning trees of a connected graph G, and let E be an edge in T but not in T dash. Then there exists an edge E dash in T dash but not in T, such that T minus E plus E dash is a spanning tree of G. So what essentially we are given here? We are given two spanning trees of a connected graph G, say T and T dash, and we are given one edge, say E, of the tree T but which is not in the tree T dash. And with this information we have to prove that there is one edge, at least one edge, say E dash in T dash but not in T, in such a way that T minus E plus E dash is a spanning tree of G. So, let us now prove it. So, assume that G has n vertices. Now, since T is a tree and E is an edge in T, T minus E is disconnected. Why? Because E is a cut edge. You know that every edge of a tree is a cut edge. So, T minus E is a cut edge and therefore, T minus E must be disconnected. So, let T1 and T2 be the two components of T minus E, right. Now, since T dash is connected, because T dash is a tree, there must be an edge E dash in T dash, but not in T, in such a way that E dash has one endpoint in T1 and the other endpoint in T2, right, because T dash is connected, right. So, with any two vertices of T dash, of course of G, there is at least one path. So, that means between two components T1 and T2 of T minus E, there is some edge that has one endpoint in T1 and another in T2, and this edge is E dash. Now, this means T minus E plus E dash is connected, else is remaining. We have shown T minus E plus E dash is connected, and now we have T minus E plus E dash has the same vertex set as T and which has the same vertex set as G, right. So, this means T minus E plus E dash is a spanning subgraph of G, right. And now, because T is a tree, you know that T has n minus 1 edges and therefore, T minus E has n minus 2 edges, and this implies T minus E plus E dash has n minus 1 edges, and that means T minus E plus E dash is a spanning tree. Now, let us look at this question: how many different trees are there on n labeled vertices? This is such kind of questions were quite important from the point of view of in chemistry there are chemical molecules and there have to be some molecules which are same, which are structurally same, and to find out such kind of different molecules which can be labeled, which can be connected with the same atoms in different number of ways, Arthur Cayley attempted graph theoretical techniques. In fact, he used the term tree first and he obtained a very important result which gives us the number of all labeled trees on n vertices. Let us look at just a very specific case. For instance, suppose you have just n equal to 3, then there are only 3 labeled trees which are A, B, C, A, C, B and C, A, B, right. So, in general we have this result which was proved by Cayley and is now known as Cayley formula. It states that the number of labeled trees on n vertices is n raised to the power n minus 2. Okay, the next concept that we shall discuss here is the concept of rooted trees. The concept of rooted tree is quite often used in computer science, especially in the development of algorithms. Intuitively, a rooted tree is just a tree with a root. Formally, a rooted tree is an ordered pair T E T R, where T is a tree and R is a specified vertex of T called the root of T. For instance, look at this tree. We have specified the vertex R as the root, of this tree, and therefore this is a rooted tree. And important property of rooted tree is that once you are at the root, you can reach to any of the leaves of the tree. So root essentially just works as a starting point for traversing a tree. Note that there is exactly one path from root to any leaf, right? There is a one path, exactly one. So this path is essential in determining many other notions, like the notion of ancestors and descendant of a vertex, or the notion of parent and child. So let's look at what these notions are. So first we see what we mean by ancestors and descendants. So consider a rooted tree TR, and let V belongs to VT. Then a vertex U is called an ancestor of V if U lies on the VR path in T. That is, if U lies on the path from V to R, then U is called an ancestor of V. So suppose here is your root and this is your vertex V, and if U lies somewhere on this path, then V is an ancestor of U. Similarly, we can define the concept of descendant. A vertex U is called a descendant of V if V lies on the UR path. Let's look at geometrically. Suppose you have this tree R, R is the root here, and look at these vertices, say A and B. So the vertex C lies on the path RA, that means the path from R to A, and therefore C is an ancestor of A. Likewise, D also lies on this path, so D is also an ancestor of A, and in fact D is also an ancestor of B also, just like C. And you can see that R is the ancestor of all these vertices. What is the relation between X and C? We can say that neither X is an ancestor of C nor C is an ancestor of X. In fact, because there is no path from root to some vertex that contains one of these two, right? Now look at these two vertices A and B. The vertex C is just one edge away from A and B, right? So in that case, C is called a parent of both A and B, and A and B are called its children. So formally the definition is here, parent and child. So let TR be a rooted tree and let V be any vertex in T. So vertex U is called the parent of V if U is the neighbor of V on the RV path, and if U is a parent of V, then V is called a child of U. For instance, again look at this rooted tree. Here we have seen that C is a parent of both A and B, and A and B are the children of C. Note that A and B have no children, and C is a parent, C is a child of D, right, and D is a child of R, and all these vertices are, they are not actual children, but they are the descendants of R, right. Now suppose you have two vertices which have the same parent, say A and B. Look at these vertices, they have the same parent C. So in that case they are called the siblings, right. So these are some of the notions which are useful for computer science applications. Another concept is of the concept of binary tree. So a rooted plain tree T is called a binary tree if every vertex of T has at most 2 children and each child is designated as the left child or the right child. So, rooted plane tree means just a tree which is rooted tree which has been drawn in a plane, right. And so, if this is a binary tree, then it has each of its vertices has at most 2 children, and one of them is called a left child and another is called the right child. For instance, just look at this tree, the R is the root here, and look at the R, the node the vertex R has just 2 children, say D and X. X also has 2 children, Y and W. D has only one children, C, one child only C, and C has 2 children, namely A and B. So, here D is the left child of R and X is the right child of R. D has only one child C, so which is the right child. C has 2 children, A is the left child, B is the right child. So, this is a binary tree. A binary tree is called a complete binary tree if all vertices in it have either 2 children or no children. For instance, just look at this tree, it is this vertex is the root here, and the root has 2 children, these 2, and this vertex has also 2 children, this also has 2 children, and in fact every vertex here has either 2 children or no children, right. The leaves here have no children. So, this is a complete binary tree. What about this tree? Is it complete? Note that this is a binary tree because each vertex has at most 2 children, but it is not complete because look at this vertex, it has only one child, right, left child, it has no right child. Similarly, look at this vertex, it has right child but no left child. So, this is not a complete binary tree, of course, but it is a binary tree. So, in this session we have discussed the concepts of spanning trees, rooted trees, and we have seen some properties of trees. These concepts are quite useful in applications like in computer science. While we develop algorithms, we need the concept of rooted trees, and so that is all in this session.